Balance of the scales, it can be challenged or expelled. Soon as somebody lost, somebody else prevails. Someone is quiet at the same time someone yells. Half full or half empty, water in the well. The half and half hypothesis, the 50-50 theory. Eerie as it may seem, check your balance beam. The half and half hypothesis, the 50-50 theory. Eerie as it may seem, yo check your balance beam.
Welcome to Le Chatelier's principle. I'm pretty excited about it, okay? Le Chatelier's principle is dependent on the equilibrium system of a reaction. Again, Le Chatelier's principle states that any change into a system will cause the opposing change of the equilibrium in order to counteract the changes. That is, whatever you do to a system on one side is going to shift the equilibrium to the other side to counteract it. All right, the equilibrium evens out both the products and the reactants on both sides. So reactants on left, product on the right. Products are what's being made, reactants is what we put in usually. Le Chatelier's principle again states that if a chemical system at equilibrium experiences a change in concentration, temperature, volume, or partial pressure, then the equilibrium shifts to counteract the imposed change and a new equilibrium is established. For this reason, when we increase the concentration, we are disturbing the balance. On this is a balance. We have 121 grams of block or reactants. Okay, on the other side we had to add weight to counteract that balance. If I add more reactants to the reaction, I'm going to have to increase that pressure on the other side to rebalance it out. In this case, we're re-establishing the equilibrium at another area. Okay, so first things first, if we're going to increase the concentration, what's going to happen is we're going to increase the number of moles available to react. So if I increase the amount of ammonia within this reaction, that makes available more nitrogen and more hydrogen to react with this oxygen. And in turn, we produce more water and more nitrogen dioxide. At the same time, if we increase the amount of water, what's going to happen is it's going to push that reaction backwards to oppose the change, okay? How we would observe this is we would observe an increase in pH if it favors the reactants, due to the fact that ammonia is a base. Okay, so bases increase the pH, right? We know that? So what's going to happen is if I add more nitrogen dioxide to this reaction, it's going to shift it backwards, and you're going to test it using pH paper or pH meter, and it's going to have an increased pH. That will demonstrate it. At the same time, if I add more oxygen, the reaction is going to push forward, and my pH is going to become more of a neutral substance, so more of around a 7, okay? The other way we can increase or decrease the concentration is we can remove a substance. So if I want to push the reaction more towards the products, I can remove nitrogen dioxide, and that would cause a reduction in the concentration of the products, which would actually force the reaction forward because we want to make more products to make up for that removal of products. Okay.
That hot, so whether or not you find the answer, it's really not the plot.
Confess that when we two must twain, although our undivided loves are one, shall those blots that do with me remain, without thy help, be me but born alone.
Pulls on the ocean, balance on one foot, that's equilibrium. Opposite.
Okay, energy changes are dependent on whether the reaction is exothermic or endothermic, but the rule never changes. If you increase energy, the reaction is going to proceed away from the energy in your actual equation, okay? If you remove energy, you're going to go towards the energy to create more energy, okay? So for example, if I have an exothermic reaction of sulfur dioxide plus oxygen producing sulfur trioxide plus energy, that's an exothermic reaction, so our enthalpy change is going to be a negative number. Our energy is on the product side, okay? So if I want to increase the energy to this whole system, so I heat it up, okay? So I heat up this whole system, what's going to happen is that's increasing the energy on this side. It's going to shove the equilibrium back towards the reactant side to counteract that energy addition. At the same time, what's going to happen if we remove energy or if we cool off this reaction, it's going to cause it to be a forward reaction, and we're going to want to get more of the product. So we're going to produce more sulfur trioxide and more energy, just so that we make up for that lost energy when we cooled it off. Okay, so just to repeat what I was saying, if we increase the energy, you're going to go away from the energy in the actual reaction. If you're decreasing the energy or making it cooler, you're going to go towards the energy in order to counteract that change and make up for the energy that we've taken out of the reaction.
It's perfectly balanced. It's perfectly balanced. It's perfectly balanced.
Pressure changes only affect gases. So the only thing you have to worry about are the G's, or the gases within a reaction. Okay, that's very important, because if you're dealing with liquids or solids, they don't count in a pressure change on the equilibrium system. Okay, so if we increase the pressure, what's going to happen is our gases are going to want to move towards the side, or our equilibrium is going to shift towards the side with the least number of moles, of total moles that is. So on this side, we have 2 total moles of gaseous products. On this side, we have 2 plus 1, so a total of 3 gaseous products. So we have a 2 to 1 ratio, or 2 to 3 ratio, sorry. So as we increase the pressure, what's going to happen is we're going to go towards the moles with the least number, or the side with the least number of moles. So we're going to go towards the reactant side, okay? An increase of pressure, because of Boyle's law, as we learned in grade 11, is a decrease in volume, okay? So as we increase the pressure, we decrease the volume. That means we have less area to move around, okay? So think of gases, which are high energy molecules, as really excited children. And you're putting them into an elevator, and you have 16 really excited children shoved in an elevator. What's going to happen is they're going to want to move out of the elevator into a more open space so that they can move around happier, okay? That's the same thing here. We're going to push, we're going to decrease the volume, so we're going to cramp this whole system together, so they're likely to make less number of moles so that they have more room to move around, okay? That's the same idea here. If we increase the volume or decrease the pressure, it's more likely that the equilibrium is going to shift towards the area with more moles, just because they have enough room to move around, so why not make more people, okay? So that is increase the pressure. They want to have more room to move around. Finally, we have adding a catalyst. Now, a catalyst, it only affects the activation energy, as you already know. So if we add a catalyst, what's going to happen is our activation energy is going to decrease, and it's going to cause the reaction to go faster. At the same time, it's only going to affect the reaction rate. It's not going to actually affect the products or the reactants. And the fact is that it actually makes a reverse reaction just as fast as the forward reaction. So it's not actually going to affect the reaction rate, or it's not going to affect Le Chatelier's principle. Oftentimes they're going to try and trick you and say, what is the effect of a catalyst according to Le Chatelier's principle? And a lot of people will think, oh, it's going to increase the forward reaction, it's going to cause the reaction to go forward. But at the same time, it is reversing the reaction just as fast, not going to affect the equilibrium. Catalysts are overrated according to Le Chatelier's principle.
Set opinions, politics and religions, clues to the past and cash and keys to the future. It's possibility and probability on who gon' execute your ass. I'm slow and analytical, some quick fast on the dash. Like heads and tails, but the head usually leads the tail. So I tell my tails from the head, cause they're embedded inside myself. Real quick, let me tell by the fact that I do know things that even out. You disbelief or doubt or even shout and leave it in your mouth. Now, how you gonna reason with grandmother nature, running Mother Earth, controlled by Father Time, who's the chaser? It's living and dying, homie, laughing and crying, dude. Crying or lying, my brother, walking or flying, fool. Now, half of you wanna find the time to shine, the other half go find